And I am very excited to present our first math chat question. I hope that we can have an exciting and fruitful chat. This actually came from a person in the other class, so it's none of your questions. The question is there a limit to what math can explain? So here's my little plan for chatting about this. I don't want to spend too much time on this, maybe 10 minutes or so. I don't know, we'll see how it goes. But I thought that everybody should chat with the people around you. Make a little group of, I don't know, 2 or 3 or 4 people. And then after 5 minutes or so, I would like to just kind of go around the room and see what each little group came up with. If you don't want to be in a group, that's all right. If you don't want to talk to anybody. But that means I'm going to ask you specifically to tell me when I'm going around the room what you think about the answer to this question. So think about, your answer could be, no, math can explain everything, like everything. In that case, you can tell us why you think that, or maybe you have an example of something you think math can't explain. I don't know. Think about it. I'll give you about 5 minutes. Go for it. Chat.
In the world. Oh, really? Because I say every night. Yeah. There's a lot about that's like the one thing well, so okay. We want to like, well, maybe your brain is like sending signals that use like you can't explain anything that's like and sometimes students are actually they go against they don't have that's good. That was good. There are obviously something we're like yeah. Is there? Oh, good.
All right, it sounds like people are done chatting. Everybody, thank you for chatting with your neighbors. I know some people don't like to do this kind of thing, so I appreciate your participation, everybody. So maybe we can go around. I'll try and like make a little list here, although I don't know what we're going to do with this list, but just to demonstrate that I care about your opinion, I'm going to write down what you say. Maybe can we start back here and go around this way? What did you say?
So we said that there isn't a limit to what math explained. We were trying to figure out things that maybe math couldn't explain. Like I started thinking about like feelings and opinions and stuff. And then he was like, no, there's still a way that you could probably put math into that. So
All right.
Math is just too involved in all aspects of our lives.
Yeah, great. Yeah, feelings. Yeah. Math don't care about your feelings, maybe. Or maybe does. Yeah, I'm not gonna try to have an opinion about everything you say. Great. What did you guys come up with?
We said that we think there is a limit. Because then we were also saying like broader things like emotions or miracles or things that just can't be explained.
Unexplainable things. The UFOs. Yeah, great. All right. Maybe by the end, everybody's going to say, yeah, what they said, but I hope that you all still have interesting things. What about you guys?
We said like something similar, but we also said that humans tend to not follow like systematic things, and like math is technically a system. Because like human nature, like yeah, we follow rules, but like we're irrational sometimes. So.
Yeah, great. Human things. I don't know who all the groups were. Like you guys.
Well, we were saying that there like is definitely like a limit, but math is also like involved in your feelings and emotions too, because like I don't know, like the amount you feel and things like that, but it's also kind of separate because it's not really like the system of math. It's kind of just like your feelings and like what's going on.
Yeah, great. How about in the back?
We also said that there's a limit because even though math is like involved in our daily lives, there's a point where it's something.
Yeah, great.
You said
What do you say?
that, like there's not necessarily a limit, like a clear-cut limit, and like it can be subjective, like a lot of things. So some people might be able to like explain certain things through math, but other people might not find that as like a valid or like reliable explanation.
Yeah, great. What about you guys?
We said that math can explain everything that's in like the natural world, but anything that's kind of like beyond that, maybe like consciousness or like stuff like that, it can't explain.
Yeah. How about math is great for science? Obviously, like math kind of does explain things in science. That's kind of the point of it on a certain level. Yeah, but other stuff maybe not. How about you guys?
We said that there's not a limit, but like as humans, we might be limited to the information that we know about math.
Yeah, great. There are human limitations. How about, were you guys part of this other group?
Oh yeah.
I don't know.
We kind of said the same thing. We said that there is a limit. Like yeah, math can be used to like reinforce opinions, but sometimes I guess there are instances where people might not rely on math.
Yeah, great. All right. Thank you all for your participation. Next time I'll start over here and go this way. Yeah, I think I agree. I mean, you don't have to value my opinion any more than anybody else's about questions like this. But yeah, I would say like where my mind goes, if someone asks me, is there a limit to what math can explain? I would say like math is very good at explaining things in science and the natural world. But when it comes to, I would say almost everything in my real life, math is not a great way to like solve the problems of my life. Like math doesn't help me to love my kids more, or like all of the things that sort of really matter to me on a human level are not things which mathematics is capable of addressing, you know. Yeah, like this kind of thing, feelings and emotions, that is more or less like immediately where my mind goes to. Like I personally really love math, and I think that mathematics is beautiful and amazing, but it's not like the lens through which I view the world. I think there's like a public idea of what a mathematician is and how a mathematician sees the world as like fundamentally different from how a normal person sees the world. But I think this is mostly overblown. Like I don't, it's like that meme of that lady with the math equations flying around her face. Like I don't think anybody is really like that, or at least, I mean, all the, you know, I know a lot of mathematicians, and they are not people who like try to use equations to analyze everything in their life. This is, to me, that's not a helpful way to go through life. If I'm doing science, obviously I'm going to use math to do it. But if I'm just like trying to work on my marriage or something, math is not applicable for that kind of thing, at least not to me. Yeah, this is an interesting question here, or a point here, that maybe math itself is unlimited, but there is at some point kind of a limit to what human beings can understand of mathematics, and that's true. I thought maybe I would share one other. So the other angle that my mind immediately goes to when I'm about this question, and this may be something that you are not aware of about mathematics, but there are mathematical questions. Mathematical questions, not only like questions of ordinary life, like how do I, how do I be a good person in general? To me, math is not applicable to that kind of question. But there are actually mathematical questions which cannot be answered by mathematics. I don't know if you're aware of this, that are unanswerable using mathematics. I don't mean questions about like, how can I love the world better? But questions of a mathematical nature which themselves are not answerable in mathematics. So there's a famous example. If you're really interested about this, you can look up. There's a question called, we now call it the continuum hypothesis. And this is a specific question having to do with different sizes of infinity, which is a thing in math. I don't know if you're aware. There are actually different sizes of infinity. And there's kind of like the smallest one is the size of, if I count numbers like 1, 2, 3, 4, 5 up forever, that is the smallest type of infinity. There's also the size of the real number line. That is bigger, and those are both infinite things, but the number line, because everything is kind of like packed in a continuum, that's a bigger size of infinity than the counting numbers. But anyway, there's this thing called the continuum hypothesis, and the question is just, are there any sides of infinity in between those two things that I just said? And this was viewed like 100 years ago, this was viewed as one of the most important unsolved problems in mathematics, and everybody was trying to prove either, yes, there is another size in between these two others, or there can be no such size. But it turned out, actually, this was figured out like in the 60s and 70s. It is provably unprovable. That means that actually somebody proved that there can be no proof that the continuum hypothesis is true, and also there can be no proof that the continuum hypothesis is false. That means this is an example of a mathematical statement which cannot be proved mathematically. So if you ask, this is also like what first occurred to me when I saw this question. Is there a limit to what math can explain? This is a hard limit of mathematics. Mathematics is unable to explain whether the continuum hypothesis is true or not. So there are even mathematical questions which cannot be fully explained by mathematics, which is, to me, one of the beautiful things about math, but very strange and interesting in my opinion. There's an old math joke. You're going to think this is hilarious. The joke is, a guy says, when I die and go to heaven, what's the first thing that you're going to say to God? And the mathematician answer is the continuum hypothesis true? You get it? Because this is something that to a mathematician is an interesting question which simply cannot be answered by mathematics. The only way you're going to get an answer to this question is to ask the good Lord himself when you go on to meet him. That's very interesting, in my opinion. Things like that. That math is like I think the traditional view of mathematics is just like, and something people tell me actually, the reason I like math is because everything, once you understand it, everything is kind of simple and there's always an answer. You just have to figure it out. But once you figure it out, you get the answer and everything's great. That actually is not a very accurate view of what mathematics is, because there are certain things, they tend to be very complicated things, but there are certain things which just straight up don't have any answer. And you can actually prove that there never can be an answer. Very strange. To me, that's beautiful. This is disappointing to some people, but I'm into it. Any further thoughts about this? Thank you for all of your chatting. I hope that this is an interesting chat that we just had. Tell your friends about the limits of mathematics. All right. Great. Let's talk some more about weighted voting then. I'm back on it. Weighted voting is what we've been discussing. This, I hope you remember, it's a thing with the numbers, right? A typical example would be something like, how about this? 6, 3, 2, 1, 1, 1. All right? Look at the numbers, and the idea is, remember that first number, the 6, is called the quota. That's how many votes have to be added up in order to actually sort of make a, you imagine this is like people trying to pass a law or something like that. And if you want to actually make it happen, you got to add up votes to 6. And the big question is, who here has the power and how much of it? All right? We last time talked about dictators, dummies, and veto power. Those are fairly extreme types of power in systems. But usually, if I just make up the numbers at random, or like these numbers in particular, I will say usually there's no dictator, dummy, or veto power. Although in this example, actually, one of those things exists. Can anybody see? I hope you remember what those mean. Dictator means that one of these guys can make it to the quota all by themselves. So that's definitely not true here. But is there a dummy or somebody with veto power here? Just to refresh our memory, dummy means they have no ability at all to affect the outcome, and veto power means you cannot make it to the quota unless you use this this particular person. Yeah?
Would one of the ones be the veto power? Because it's like you can't get to 6 without them.
I think you can get to 6. This is an interesting and sort of somewhat confusing thing, but you could ask yourself, like, the first one here, does this one have veto power? That means, do you need to use that one in order to make it to 6? And the answer is no, because you can use one of the other ones. So you have to think of these as individuals, even though they have the same numbers. You do have to use one of the ones, but what about the 2? Do you have to use the 2 in order to make it to 6? I think you do, because the other ones, if you don't use the 2, oh no, I think you don't. The other ones, if you add them all up, you actually can get to 6, right? So you don't need the 2. What about the 3? Do you need the 3? I think you do need the 3. This is what I was thinking of before, because if you add the others up, you only make it to 5. So here, the 3 has veto power. All right. But generally, if you just make up the numbers at random, certainly there's probably not a dictator, and usually there aren't dummies or veto type people otherwise. And so what we want is, we want a better or a more general way to measure the power. Like in that example, the 3 has veto power and the others don't. So I can immediately say the 3 is more powerful than the other ones. But exactly how much more? And for example, what's the relationship between the 2 and the 1? Is the 2 like just the same as one of the ones? Or is the 2 actually more powerful than the ones? It's harder to say, to answer questions like that. We want a more general way to measure the power of each. And there's actually 2 different ways to do this that we're going to talk about. And there are many other ways that we're not going to talk about, but these kind of measures, this is called a power index. That is some specific way to measure the power of each one, like in terms of like percentages or something. Like I would say something like 3 in this example, maybe 3 has 50% of the power, and then the others each have, however much you need to add up to the other 50% from the other. Something like that. This is called a power index, and we're going to discuss 2 of them. And the first one that we're going to talk about today is called, unfortunately, the 2 different ones we're going to talk about both have like a guy's name on it, and you just have to remember which is which. This is actually 2 people. This is called the Shapley-Shubik. Those are 2 people's names. Power index. the Shapley-Shubik power index. So this is a specific way to measure exactly how powerful each of the different people in the system is, all right? So I will just do a little, this is not really hard to do, although it will take you a few minutes and you have to sort of think very carefully when you're doing it, but each individual step is not hard. In the case of this particular example, I am going to give these voters names. So I'm always going to call them A, B, C, D, A, B, C, D, E. Usually, so far, I have just been like referring to them by their numbers, but you can see that like there are 3 different ones here, but it is important to think of them as different individual voters, even though they all have the same weight. So I'm not just going to call them 1 each time. We have to actually think of them as being 3 different voters. And we imagine that they vote, imagine they are voting in some particular order. Now in real life, when you vote, it doesn't matter what order everybody votes in. But for the sake of calculating this thing, the Shapley-Shubik power index, I'm going to imagine that they are voting in some particular order. Like, for example, how about, I'm just making this up. How about B, A, C, D, E? That's one particular order that you could imagine these voters cast their votes in. And the idea behind the Shapley-Shubik power index is power is measured by, this is something that hits home to me. I remember, for some reason, I remember this sort of slightly traumatic incident in my childhood when I was on a little league baseball team, and I was always bad at baseball, but for some reason I was really into it. Like I really wanted to do it, and I remember my parents would ask me like, "You sure you want to play baseball again this year?" And I was like, "Yeah, I'm into it," even though I was terrible. But anyway, there was one game where I actually managed to score a run, and then later on in the game, the score was tied, and then somebody else on my team scored again, which made us win. And everyone was like, "Oh, this kid, yeah, he got the winning run." And I was like, okay, but I also scored a run earlier in the game, and mine was just as good as his. Like, shouldn't I get some credit for that? But I didn't. The Shapley-Shubik is the same idea as that. So the power is measured by who casts what they call the pivotal vote. This is like that other kid, the one who actually made it to the winning result, all right? So somebody whose vote didn't tip the margin doesn't really count as much for this kind of power measurement. Who casts the pivotal vote? That is to say, at which point exactly is the quota met? All right. So when I see B, A, C, D, E, all right, I'm looking just specifically in this order. The numbers, of course, here, if you remember from up there, the B is 2. So I'll just write the numbers here also. 2, 3, 1, 1, and 1. And now, if you imagine they vote in that order, the quota is 6, of course. At which point is the quota actually met? Can anybody say? You start with B first. B is only 2, so that doesn't make it to 6. Who's the one that actually makes it to 6 here? Yeah? It is C in this case. So here, C is the pivotal voter. That's because, now this is, once you know what you're doing, this is very easy to do in your head, but if I'm trying to explain the details of how it goes, I would say B is 2, and this is not making it to 6. All right, and then B and A that would be 2 plus 3, which is 5. And again, this is not making it to 6. But when I do B, A, and C, this is 2 plus 3 plus 1, which is 6. So C makes it to 6. All right? This is what you're doing when you decide who is the pivotal voter. You decide at what point, sort of reading from left to right, at what point does it actually make it to the quota? All right? Let's just look at one other. So that's one particular ordering, but I just more or less chose that particular ordering at random. There's nothing special about that. Yeah?
So what's like the reason behind switching like B and A? Because like, is there like, are we supposed to just like switch them because I want somebody else to be pivotal?
Yeah, right. So this C is the pivotal voter in this particular arrangement. But if I had made a different ordering, then somebody else would be the pivotal voter probably, right? So, and this I just consider this voter, this particular order more or less at random. And I'm about to say, what if we choose a different order? So what about, how about in, let's say, C, E, B, A, D, right? In this ordering, who is the pivotal voter? All right, again, I'll write down the numbers. The C is a 1, the E is a 1, the B is 2, the A is 3, and the D is 1, right? Those are the numbers for those particular ones. And again, you can more or less do this in your head, although you have to kind of concentrate, or at least I do when I do this. You should be adding these numbers up from left to right and identifying at which point do we actually make it to 6 or possibly beyond 6. What do you think? I think it is A. Yeah, as I go left to right here, I see 1 first, which doesn't make it. Next I see 1 plus 1, which is 2. Again, that's less than 6. Then I go 2 more, that's 4, still less than 6. Then I go 3 more, and then it goes up to 7, and that actually is meeting the quota. So here, A is pivotal. That's because if you take just the first 3 together, they do not make it. That's only 1 plus 2, which is 4. But additionally, adding in the A, it goes up to 7. So here, A is pivotal. I'll just say A makes it go to 7. All right, so this is how to find the pivotal vote. It's A in that example. All right, now, as she said, and as I said, who is pivotal really depends on what the ordering is. So the fact that, for instance, A is pivotal here, that means A has some amount of power in this particular order, but C was pivotal here, that means C has some amount of power in this particular order. How do we judge who has sort of the most power overall? You just do this for every possible ordering. And then this will tell you, in all possible scenarios, who has more power and who has less power. All right, so that's the idea behind this Shapley-Shubik, which I'm pretty much always going to write as SS. That's the Shapley-Shubik power index. Considers all possible orderings. This is slightly annoying. There can be a lot of different ways of rearranging the voters. But anyway, considers all possible orderings and then count up who is pivotal in each. Right? And like in this particular example, because the A has 3 and the C has 1, the A is going to be pivotal a lot more often than the C is, because it's about who has the capability of pushing us over the threshold. And somebody with more points is going to do that more often than somebody with less points. That's the idea behind this Shapley-Shubik. All right, can I just say a little bit of terminology here? Each ordering, actually that's not the word that's typically used here. Like for instance, B, A, C, D, E. This is called a voting permutation. that word permutation is something that is a common word in mathematics. It just means some kind of reordering or rearrangement of a set of things. So each ordering like that is called a voting permutation. And then in each permutation, so the idea is we consider all possible permutations and then count up who is pivotal in each of them. This is not that hard to do, although it will take you a few minutes. Let's just try one example. I got a couple, and then I got one for you to try, although I'm not sure we're going to get to that today. But I got one. So this would be like a typical, homework or test question. Find the Shapley-Shubik index. For this example, I'm going to go 16, 12, 10, 5. All right. So I'm going to start by assigning names to these three candidates. And I'm always, unless you have a better idea, I'm always just going to call them A, B, C, D, whatever. And I'm going to make a giant chart here. You might want to turn the page in your notebook if you're towards the bottom, because I'm going to make a big chart here. And the chart involves listing all voting permutations. So I'm going to make one sort of column in my chart here. Perms. These are the permutations of A, B, C. Now there are three voters here. You need to write down all possible ways to rearrange them in some order. This is a little annoying, but I'm going to try to do sort of like some kind of alphabetical order. I don't know. A, B, C is first. And then there's one other permutation which has A first, and that would be A, C, B, right? I'm going to try to be systematic in the way that I write these down. That's the only two ways that you could start with A. Now let's write, there are two ways that you could start with B, right? So I could go B, A, C, and I could also do B, C, A, right? And then there's two ways that you could start with C, and that'll do it. So it could be C, A, B, and C, B, A. All right? And those are all the possibilities. This is generally true. Maybe I'll just write a little sidebar here. For three voters, there's always 6 perms. So this, I mean, you don't have to memorize that, but probably you will end up remembering this basic fact just to make sure you get them all. There's always going to be 6 of them if there are three voters. Okay, those are the permutations. Now, just to help us out, I'm going to write down the weights. This, if you really know what you're doing, you might be able to skip one or the other of these steps, but this is the way that I'm going to write it. So I'm just writing the weights of these three in that particular order. So this is 12, 10, 5. This would be 12, 5, 10. I'm just writing the weights in the same ordering of the permutation in each row. So BAC would be 10, 12, 5. Then I have BCA would be 10, 5, 12. CAB is 5, 12, 10, and then 5, 10, 12. That's the last one. All right? I hope you are agreeing with me that this is not really hard. It will take you a few minutes to write down all the details, though. Okay, and then the important step. All of this is, I haven't really had to think very much about anything here. The important step is right here. You have to go line by line and decide in each case who is the pivotal voter. And this involves looking at these numbers from left to right and adding them up in your head and deciding at which point do we get to 16 or more. That's what you're looking for here. So in the first one, 12 is not to 16, but 12 plus 10 is 22, which does meet the quota of 16. So I'm going to say the 10, I usually sort of underline it. You could circle it, whatever you like. The 10 is the pivotal voter in this case because 12 doesn't make it by itself, but 12 plus 10 is 22, which exceeds the quota. So the pivotal voter for this one is B. All right? And then we're just going to go down the list and decide each time who the pivotal is. And this will let us see who is the most powerful and who isn't. So in the next one, 12 and 5. I believe it's the 5 that makes it to the quota in the next one. This would be C, right? The next one, 10 doesn't make it, but the 12 does make it, and so that's A. The next one, 10, can anyone say in this one? What do you think? You go left to right, adding them up. At which point does it get to 16 or higher? I think it's the 12, yeah. The 10 doesn't. 10 plus 5 is 15, which is not enough, but the 12 makes it. So the 12 is A, right? Next, I see 5, 12, and 10. It's the 12 there, which is A. And at the bottom, 5 and 10 is not good enough, but the 12 makes it, like so. All right? So I hope that you agreed. B and C are each pivotal once, but A is pivotal 4 times. All right? This means in terms of being able to make stuff happen, A is much more capable, right? In many more scenarios, A is the one with the power. There are some scenarios in which B and C have the power, but not very many. All right? This is basically the end of the work for the Shapley-Shubik. Now, technically, you want your answer to be a bunch of numbers. So, and the way you calculate the numbers for each one, and I didn't tell you this before, but the Shapley-Shubik for each one is a fraction. And the fraction is always the number of times they are pivotal divided by the total number of permutations. All right. So in this particular example, the Shapley-Shubik power index for A is 4 out of 6. There are 6 total rows in the chart, and A is pivotal on 4 of them. For B, it's 1 out of 6, and for C, it's 1 out of 6. And this, you know, if you're doing a homework or a test question or something, this is your actual answer. And this is specifically how much power does each person have in the system. All right, these are fractions. It is often nicer if you're, you know, if you're showing this to your mom or something. She might not like fractions like that, but you can use your calculator and convert these into percentages. Like if you just do this 4 divided by 6 on your calculator, that's 2/3 also. I don't care about that. This is 0.66 repeating, right? 1/6, this is 0.16 repeating, and this is also 0.16 repeating. And so you can think of these as percentages, right? You can say A has 66% of the power, B has 16%, and C has 16%. All right? So it's a great, nice little, you know, it gives you a very, very nice looking answer, in my opinion. It tells you exactly the percentages of power for each of the people. Any questions about that? On your tests or whatever, since you're not using calculators, I would expect you to just leave your answer like that. I don't care if you simplify the fraction. 4/6 is the same as 2/3, but I don't care about that. Any thoughts about that? I think we got time for another. Let's just try another example. This is how you do the Shapley-Shubik. It takes a few minutes, but individual steps are not so difficult. Let's try the Shapley-Shubik for this one. 12, 8, 7, 1. All right, so we begin by giving them names, A, B, C. I'm going to write down all the perms. This is really exactly the same list as the previous example. So it's ABC, ACB. Those are the 2 that start with A. Then I have 2 that start with B. They would be BAC, BCA. And then starting with C, I got CAB, CBA. And then the weights. Writing the weights again in those particular orderings. So ABC is 8, 7, 1. ACB is 8, 1, 7. BAC is 7, 8, 1. Then we got 7, 1, 8. And then we got 1, 8, 7, 1, 7, 8. All right, those are the weights. in those orderings. And now this is the first sort of hard step, in my opinion. It's not really hard, but you do have to kind of concentrate. Tell your roommates to turn the music off for a moment. I have a hard time doing this in my head. If someone's talking to me, you're probably trying to do it right now, but I'm talking, and it's not easy. 8 and 7 is 15, so that 7 is the pivotal in this case, which is B. What do you get for the next one? Who's the pivotal in the next one?
7.
I think it's the 7 again. Yeah, 8 and 1 is only 9, so you got to go to 7 to make it. That's B. 7, 8, and 1, I believe it's the 8, because 7 and 8 is 15, so that's A. 7 and 1 is not enough. You got to go to 8 in that one. 7 and 1 is only 8, so that's A. 1, 8, and 7. Who is it in the 1, 8, 7?
7.
It's the 7. Yeah, 1 and 8 is only 9, so you got to use the 7. That's B. And then finally, 1 and 7 and 8. 8 is the pivotal in that case. That's A. All right. So my final answer for this one would be A has 3 out of 6, which I don't even need my calculator. This is 50%, right? B also 3 out of 6, 50%. And C, 0 out of 6, 0%. 0 out of 6. All right. Very nice, in my opinion. You can actually see what's my interpretation of this. Apparently, C is a dummy. C has no power at all in this system. And this is a foolproof way, although it takes a few minutes to do it, a foolproof way to actually calculate that somebody is a dummy, right? The fact that I got 0% means that C has no power, and I got 50% each. That means actually in this system, A and B have equal power, even though 8 is more than 7. They still have the same amount of power in this particular arrangement. All right? I think there's enough time for you all to try one. I got one. See what you feel. This is, I'll try to keep that one on the screen since most of the details are the same. How about 12, 7, 6, 5? See if you can work that one out. You should make a big chart with the same perms, different weights, and pivotals, of course. All right, can we do this just because we have to leave soon? I see some people finished, some people almost. So anyway, I'm going to take my same list of perms here. Copy this down here. Now the weights in those same orders is 7, 6, 5, 7, 5, 6, 6, 7, 5, 6, 5, 7, 5, 7, 6, 5, 6, 7. Right? This is the order in which I write the permutations. You might have written yours in a different order. That's fine. And then we got to do the pivotal voters in each case. Pivotal. We have to make it to 12 here. So in the first row, 7 is not pivotal, but 7 and 6 is 13. So the 6 is pivotal there. So this is B. Actually, is it always the second position that's pivotal in this case? Certainly the first one is never pivotal by itself. 7 and 5 makes 12, so the 5 is here. 6 and 7 is 13, so the 7 is pivotal here. The next one, 6 and 5, that's only 11, so actually you have to go to the third one to make it to 12. So the 7 is pivotal there. I hope that folks worked it out. 5 and 7 makes 12, so the 7. And then the very last one, 5 and 6 is only 11, so I got to take the 7. So who's pivotal in each case? It was B first. The next one is C. And then all the other ones are 7s, which is A. So this is A. All right? I hope you got something like that. Yours might be in a different order, but you should have the same amount of A's. There should be 4 A's, 1 B, and 1 C. And so my final answer is A is 4 out of 6. B is 1 out of 6. C is 1 out of 6. All right? Some people, as I was walking around, I saw this a couple times, and I see this on the homeworks sometimes. You may be tempted, just because of what we've been doing earlier in the course, you might be tempted to say, A wins, but this is inappropriate to say. This is not a contest to see who wins. These are 3 different voters trying to make something happen. The purpose of this whole thing that we're doing is to measure how powerful each one is. So the answer is, in informal terms, you could write this as percentages, or you could also say something like A is 4 times more powerful than each of B and C. And B and C have equal power, even though this is not something easy to tell by looking at these numbers, right? These numbers are only 1 off from each other, but it turns out the 6 and the 5 have equal power, but the 7 and the 6, the 7 is actually 4 times more powerful than the 6 in this system. All right, that'll do. Hope you all have a good weekend.